and try and ask questions and get help, all right? Yeah. So, all right. This is how are y'all feeling? I mean, y'all feeling motivated? Do you feel like you're going to advocate for yourself? Do you have time? You know, are you going to form groups? That's why I did that first quiz. I wanted just right off the bat for you to talk to the person next to you, okay? I can't force you to be in groups. I can't. But in my office, okay, in my office area, there is a room with whiteboards that if you form a group, I'm happy to reserve that room for you all semester long. I'm happy to join you in that room if I can work it into my schedule. You know, if you have a group of students, it can't just be like 2. I need a little bit more than that, maybe like 4 or 5. If y'all get together, I'll do everything I can to help like make that happen and be present in there for you. But you all have to do that. And before COVID, I mean, it was just normal for me every semester that I'd go into that room in my office, this conference room, and I'd have, you know, students floating in and out of that room all during my office hours. I'd have groups coming in, groups coming out, and so I'd like to get back to that, but I can't force you to do that. So, and these tables aren't very good for forming groups, are they? So we'll have to figure it out. All right, what is Cal 2 about? So let's talk about what the actual Cal 2 is. Well, real quick, what was Cal 1 about? I mean, if you could summarize Cal 1. Derivatives, okay? Tangent lines, right? Limits. Okay, so you start Cal 1 with limits. And then from there, you talk about the difference quotient and the slope of a tangent line. And then you get to the idea of the derivative, and then you do some other things, right? You do other things you don't like so much, like implicit differentiation, related rates, optimization, right? All that stuff. Okay. But the main idea of Cal 1, derivatives, right? Differentiation. Slopes of tangent lines. Cal 2 is really broken up into 3 parts. Okay? There are 3 parts to Cal 2. Part 1 is called techniques of integration. So basically, we're going to spend the first couple of weeks in this class just making sure we know how to find the antiderivative of a function. Now, in Cal 1, you should have talked about antiderivatives a little bit at the end of the semester. If you didn't, it's okay. I'm going to kind of treat it like you never saw it. So there's going to be a bit of an overlap here. And then the second part of this is going to be applications of integration. So once we learn how to find antiderivatives, we're going to see how we can use that to do things. So we'll be finding areas, which again in Cal 1 you probably did. So like if you're given 2 curves, you know, like this straight line and this parabola, can you find the area between the 2? Then we do things like, hold on. Okay, so you see these 2 curves? So what we're going to do, I need my glasses, I can't see this. What we're going to do is we're going to, hold on, region, here we go. We're going to imagine that this curve that we're looking, these 2 curves that we're looking at, we're going to imagine that they actually live in 3-dimensional space. See that? And we're going to take this and we're going to wrap that whole region around the x-axis like that. See that? 3-dimensional figure. And the question will be, what's the volume of that object? Okay? We will need to know what antiderivatives are in order to do this, all right? And then we'll do other things. I mean, there's a lot of things we're going to do. We're going to wrap it around different axes. Let me see if I can do this one. Washer region. Okay. Yeah, I won't get into that. Let's not even. So we're going to do areas, volumes, then we're going to talk about arc lengths, surface areas, centers of mass, moments of inertia, hydrostatic pressure. So the last 3 there, center of mass, moment of inertia, hydrostatic, those are all like specific applications of antiderivatives or integration. So, you know, we'll do that. And then we get to, that's like the second third of the course. And then we get to chapter 8, which I know a lot of you have heard about. Yes? Have you all heard about the dreaded chapter of series? Yes? Series is hard, okay? For most students, it's hard. And the reason it's hard is because, well, it's just different. It's just different. Like, you've never really seen math this way. You've never looked at it this way. Even in high school, unless you did calculus BC in calculus, or in high school, unless you did that, you probably didn't see this. So, and even if you did calculus BC, they look at it through a different lens than we look at it here. So, I won't get into this right now. Okay, I don't want to talk too much. I don't want to get the carriage in front of the horse right now. Just know that this is going to be the second third of the course. All right, we good? Y'all look really like you're just ready to get going on this, right? You're like, come on, stop talking. Let's get into the math. Yeah? Here's my plan. I'm going to see how this works. I want to, that screen over there just duplicates this screen, right? But it's really kind of small and hard to see, especially over here. My plan is to raise this up, turn off this projector, and use this board the whole time. And then if I need to refer to like some graph or animation, I'm going to project it there. That's the plan. Let's see how that goes. If anyone back over here or anyone has trouble seeing that, please let me know, all right? All right, let's try this. I did this. I experimented before the semester started. See if I'm successful. I even had to make a little thing so I could press this button. It did not come with the room. No, IT doesn't ask us anything. They don't ask us what we want. They just do it. Yeah, no, I have it. It attaches to my tripod. So I'm going to keep this with me all. The white one? Yeah, I put those in all the other rooms. That's for adjusting the up and down. Yeah, I put them in all the rooms. But this one's mine. I'm moving this one around.
Because Mark told us that somebody went and made one for all the rooms.
Yeah. It's just PVC. All right, you ready? 3.5. This is great. I can't wait to not worry. All right, so look, all of the notes that I project over there, everything I project over there, those notes are available in Canvas. Okay, the notes are available in Canvas, all of these notes. You can get through under the Files link in Canvas. Feel free to print those out. Okay, you can print them out, or you can just watch what I do in class and then go refer to them electronically later. Totally up to you. If you print it out, it's a lot, so you don't necessarily have to. All right? But I'm gonna blow through those quickly because I'm not expecting you to write those down. That's all already for you out there. All right? So we're starting with 3.5 inverse trig functions. And I think the best way to start this, and to give you an idea of where we're headed with this, is to just remind you, recall what you learned in Cal 1, right? So that the derivative of sine x, right, is cosine x, right? And there are 6 trig functions that you learned the derivatives of in Cal 1, right? There are 6 of them. The next one is cosine, right? We all know that the derivative of cosine of x is what? Negative sine x. And then those two you better know, right? You better know those two. And then the next one is tangent. That one you should know. Secant squared x, good. Those should be memorized. As a Cal 2 student, those 3 should be memorized. The next 3, yeah, you should do it. You should try. So let's go with secant next. So what is the derivative of secant x? Anyone know? Without looking at a formula sheet? Secant x, tangent x. All right. Now I'm going to stop here, okay? Because I'm just going to waste time. These are in your formula sheets, aren't they? So on our files, I want to show them to you. on our formula sheets, and I know that's hard to see over there, I'm going to zoom in. In our formula sheets, on page 5 of one of our reference sheets, there are the derivatives, and this section right here, trigonometric functions, derivative of sine is cosine, derivative of cosine is negative sine, tangent, and then here are all the rest, right? So you have those available to you on a test. The question now, or what we're going to talk about now, is what about the inverse trig functions? We study the inverse trig functions in pre-cal, right? In pre-calculus, you learn about sine, cosine, tangent. Don't think derivative right now. Just think the function sine. You graph sine, you graph cosine, phase shift, all that stuff. You do that in pre-cal. What we're interested in now is if you look at the inverse trig functions. So if you take the inverse of sine and you ask the question, what is its derivative? What is it, right? So you had 6 trig functions from pre-cal, sine, cosine, tangent, secant, cosecant, cotangent. All 6 of those have derivatives. Then we have each of those trig functions has an inverse and should each have a derivative as well. And that's what this section is about. What is the derivative of these inverse trig functions? So what's the derivative of that? What's the derivative of this? Right? What's the derivative of tangent inverse? And so on and so forth. There's 3 more, excuse me, there's 3 more, right? There's 3 more. Secant inverse, cosecant inverse, cotangent inverse. What are their derivatives? All right, so let's start by I'm going to show you the derivative of this. We're going to figure out what it is. All right? We're going to do it by hand. I could just show you the formula, but there's no fun in that, right? We want to see where it comes from. So what we're going to do is this. Let's find the derivative of the inverse sine function. All right? I want to find, this just means I want the derivative, right? Another way I could write this is to say, and I'm just doing this in case you had different notation in your calculus class, find the derivative with respect to x of the inverse sine function. Does that notation look familiar as well? Okay. Or another way I could have wrote this, the derivative with respect to x, I could have written arc sine x, because that's arc sine. If you write arc sine of x, that's the same as writing this. They mean the same thing. So I'm just putting that up just in case you saw different notations. All right? So you ready? Let's see if you can follow how I'm going to find the derivative of this. I'm going to start out like this. I'm going to say let y be equal to the inverse sine of x. Okay? I'm going to call this function y. And now what I'm going to do is try and find y prime, right? I need to find the derivative. I don't know what it is. So the next step is actually going to be, just because I know where I'm going with this, let me do the step and see if it makes sense to you. I'm going to take sine of both sides of this equation. Okay, this is an equation, y equals the inverse sine of x, right? I took sine on both sides of the equation. I'm allowed to do that because sine and sine inverse, if we have proper domain restrictions, this is the part I'm kind of skipping because this is pre-cal. Like, if you're ever talking about an inverse sine function, you've already had a domain restriction, because you can't have an inverse unless you restrict a domain. Now, in your notes, I talk about this. So if you need to go back and review this, it's all here. What are one-to-one functions? How about the sine function? If we have an inverse sine, we have to restrict the domain between negative pi over 2 and pi over 2. So I'm not going through all this, but I'm just mentioning that it's perfectly legal for me to take sine on both sides here, because I've already assumed that the sine inverse function exists, so the domain restriction is implied that I'm allowed to do this. Now, why would I do this? Why does this do anything for me? Those two go away, right? And you just get x on the right-hand side. So it's kind of weird. We started out with y is the inverse sine of x, and then now I've got sine of y is x. Now how does that help me? What I'm going to do now is I'm going to differentiate both sides of this equation with respect to x. Now, reminding you of what this was in Cal 1, this step right here is me doing implicit differentiation. This is a Cal 1 idea. I'm differentiating both sides of an equation with respect to the variable x. With respect to x, right? So this is where I'm going to ask for volunteers. Who wants to tell me what the right side of this is? 1, okay. Left side? Left side's the harder one.
Cosine of y is dydx.
Okay, cosine of y first, right? So you're saying, hey, what's the derivative of sine of something? Cosine of it, right? So you do that, and then times chain rule. Was that you, sir? What was your name?
Oscar.
Okay. And then you said what now?
dy dx.
dy dx. That is chain rule. Taking derivative of sine of something is cosine of it. Then times the derivative of the argument of the sine function, which is derivative of y, with respect to x, which is dy dx. You could write y prime here if you want instead of dy dx. It's fine. But you have to get the chain rule. If you don't get that chain rule, then it's going to be wrong. And now we're there because all we have to do is solve for this. This is what we're actually trying to find, dy dx. So what I'm going to do is I'm going to divide both sides by cosine of y. 1 over cosine y. Jeez. 1 over cosine of y. And isn't that, what trig function is that? 1 over cosine is?
Secant.
Is it secant? It's secant, right? Secant y. Any questions on that? Started out by saying, hey, I want to know what the derivative of arc sine of x is. And then said, well, I don't know what it is, so let's call this thing y. I did that intentionally so that I could bring in sine on both sides. Then I have this equation. I differentiate with respect to x, solve for dy dx, and I get my answer. Let's check our formula sheets to see if we did it right. Oh, where are my formula sheets? Right here, formula number 19. I know it's hard. I'll zoom in. I don't know if I can zoom in anymore. Let's see. There we go. Formula 19. The derivative with respect to x of arc sine of x is what? Oh, what the hell? First day, I already made a mistake? This is in terms of y, isn't it? What's that in terms of? X. See, we have the answer, all right? But the problem with this is that the answer is with respect to y, not with respect to x. I wonder if there's a way we can get this back to be in terms of x, not in terms of y. Understand? So what I'm going to do now is a critical step in the problem. I'm going to go back to this piece right here. Right there. And what I'm about to do is so important in this class, at least for the first few weeks. I'm going to use that information in red to create what's called a reference triangle. Let me do it, and then we'll talk. I'm going to create a reference triangle. I'll just draw a triangle, because that's cute. All right, I'm going to create a reference triangle. It's so nice to be able to use so much board. So when I do this reference triangle, I'm going to use this information right here to draw a triangle. And I'm going to draw a right triangle. So I'm just going to draw a right triangle. And then sine, if I ask you for sine of an angle is which side over which side? Opposite over hypotenuse, right? Opposite over hypotenuse. So I'm going to look at this x as being an x over 1. Isn't that a fraction, right? X over 1 is, I can look at x as being x over 1. So if I now use this information to draw my triangle, my angle is y. My angle is y. my opposite is x, and my hypotenuse must be 1. All that triangle is a visual representation of that equation. That's all it is. It's just a way to visualize that equation, yes? Now the reason I'm doing that is because I want to know what secant of y is, right? Secant of y is the reciprocal of cosine. So if I knew what cosine of y was, I would be able to answer this, or to get it switched over to x. But I can figure out what cosine of y is on this if I can figure out the adjacent side of the triangle, which I can, can't I? Because I have two sides, I can always get this third one. So let's call this side A, and let's go solve for A. Pythagorean, right? A squared plus b squared is c squared. That's just a squared plus x squared is 1. Let's solve for A. Subtract x squared on both sides. Last step, square root both sides, right? Now technically I should take plus or minus, shouldn't I? I should. If I'm the one who actually comes in and square roots both sides, I need to do plus or minus. But because A is this side of a triangle, I'm just going to take the positive answer. And that's what A is, right? Square root of 1 minus x squared. So there's a few things we can do now. Back here, secant. Secant is the reciprocal of cosine. Cosine is which side over which side? Adjacent over hypotenuse, right? That's what cosine is. So secant should be hypotenuse over adjacent, right? So if I take the hypotenuse of this triangle and divide it by the adjacent of this triangle, that's what secant of y would be. So take the hypotenuse, divide by that, and we get the derivative of arc sine of x in terms of x, right? See, our answer has x's in it now, where when we did the secant y, it was correct, but it was in terms of y, not x. And that matches what's there, right? Who has a question? The reference triangle is a big deal, all right? We're going to need reference triangles in this class. Let's do another one, all right? Let's do a harder one. I usually in my classes, I'll show you how to do it for inverse sine, then I'll do inverse cosine, inverse tangent. Let's try one of the other ones. What do you say? Yeah? I'll leave those as an exercise for you. Let's find the derivative of the inverse. Let's go with inverse cotangent. So cotangent inverse of x, I want us to find its derivative. Let's see if we can follow the same format that we did here. Okay, let's follow the same kind of layout. So what first? What's that? So y equal to the inside of that, right? So let's let y be equal to cotangent inverse of x. Okay. I've done that because now I would like to operate with this as an equation and do something to both sides, right? So what now? What on both sides? Tangent. Not tangent, cotangent on both sides. So I'm going to do cotangent y equals cotangent of cotangent inverse of x, right? So you're always just going to come in with the inverse of whatever that was. Here it was sine inverse, so I brought in sine. If it was cosine inverse, I'd bring in cosine, right? If it was tangent inverse, I'd bring in tangent. That has the effect of killing off everything on the right and leaving us with just cotangent of y equals x. Now we can differentiate that, right? Implicitly with respect to x, right here. This step right here, implicit differentiation. So I'm going to take the derivative with respect to x on the left side. and then the derivative with respect to x on the right side. Now, if you don't know what the derivative of cotangent is, here's your formula sheet. The derivative of cotangent of something is negative cosecant squared of that something. So my left side is going to be negative cosecant squared of what? Of y. And then the chain rule, right? So you need times the dy dx. That takes care of the derivative of the left. And the right is just a 1. Now what?
Divide both sides by negative.
Yep. We're going to isolate the dy dx by dividing both sides by negative cosecant squared y. So dy dx is going to be 1 over negative cosecant squared y. But wait a minute. 1 over cosecant is actually just what? What is the definition of cosecant of something? Cosecant x. Cosecant of x is 1 over sine x, right? That's what it is. So similarly, 1 over cosecant of x is equal to sine x, isn't it? The reciprocal of cosecant is sine, right? Because cosecant is the reciprocal of this, so it works the other way around. Flip this over, flips that over, right? What I'm getting at is how could I rewrite that? Negative sine squared y, right? That is equivalent, this expression right here is equivalent to saying dy dx equals negative sine squared y. People have brought to my attention that my sine looks like an SW, and no matter what I do, I'm never going to be able to fix that. It's hardwired into my nerves, and there's just no way I'm changing it. That's a sine, S-I-N. I just do it so fast it looks like a W. Does it? Yeah. Sorry. That's sine. Any questions on that step? That is the answer. But just like over here, remember it was in terms of y? We would like to have that in terms of x. And so what do? Just reference triangle. Where's my reference triangle based off of? Out of all this stuff, where's the reference triangle going to come from? Cotangent y is x. Right here. That's what it's going to, I'm going to create my reference triangle from this. So let's do that. Reference triangle here. I just draw a right triangle. The angle is always going to be y. Okay, that's our angle. Oh my God, is it already? Holy moly. Wait a minute, we go till 10:40, right?
Yeah, so like 10 minutes.
I know, we only have 20 minutes. I was like, man, I'll get through 3-5, no problem today. I yapped too much, sorry. Okay, so here's this thing, right? And now this over here, I'm going to look at this right side, x over 1, as being the ratio of two sides. But what is cotangent? Cotangent is which side over which side?
Adjacent over.
Yeah, so if you forget this on our formula sheets, if you forget, you're just having a bad day and you forgot, somewhere in here is our pre-cal stuff. Here we go. There it is. Reference page 2. There it is. Right angle, trig. Cotangent is adjacent over opposite, right? That's what it says. So according to this is adjacent and this is opposite, right? Adjacent and opposite. So adjacent here is this and opposite is this. Now we need to know, what are we trying to find? I've forgotten it. We want to know what negative sine squared of y is. So I need to know what sine of y is. And then I'll square it and then I'll make it negative. So I'm trying to find sine of y. Sine requires opposite and hypotenuse, but I don't have the hypotenuse yet. I'm going to get the hypotenuse by calling this, let's call it h. How about that? You call it c if you want, whatever. Call it h for hypotenuse. Let's solve for h. Pythagorean, right? Pythagorean. X squared plus 1 squared is h squared. X squared plus 1, this is square root, right? Square root of that is h, just square root on both sides. And that's what h is. So I think I'm ready for my answer. This is negative. Okay, what would sine of y be? So 1 over this, right? So 1 over that? So I'm going to put that there. 1 over the square root of x squared plus 1, right? That's what sine of y is, right? But I have to square it, don't I? So I need that squared. You would not square the negative though, right? This squared is acting on the sine only, not on the negative. So this would now become, well, when you square a fraction, you square top and bottom, right? So this is negative. 1 squared on top is 1. And when I square the square root on the bottom, it goes away, right? So I just get negative x squared plus 1. That is the derivative of cotangent x. Sorry, cotangent inverse of x. Questions? Do you see that you could do this for the others now? Like cosine inverse, tangent inverse, secant inverse. You would do the same thing. Derivative, right? You set up the equation, both sides, implicit, reference triangle. So now, we have 6 new derivatives. I've shown you 2 of them, right? I've proven 2 of them to you, but there are actually a 6 total. And I'm not going to prove all 6. You could do that as an exercise on your own. In your homework, you're asked to do 2 more of these, prove 2 more of these. But let me get to where they are in your formula sheets. Here we go. The 6 inverse trig function derivatives right there. All right? Right here. I proved the first one for you, and I proved the last one for you. Those are the ones I proved. The ones that we're going to see the most in this class are formulas 19, inverse sine, the one I just did, and formula 21. Formula 21 is so